So we all remember the chain rule. We talk about it a lot. Every time we take any derivative, we always have to remember the chain rule. Remember, the idea is that when we're taking the derivative of a composition of functions, this time we have the inner function of 7x minus 9 and the outer function of raising something to the 1/3 power. We've got an argument that doesn't change. The inner function doesn't change. So the first thing we do is we strip out the outer layer here. We do the power rule with the something raised to the 1/3 power. So the power rule tells us to take 1/3 and pull it out front and drop the exponent by 1. So 1/3 minus 1 is negative 2/3. But what do we put in here? Well, the argument never changes. So if it was 7x minus 9, it's still 7x minus 9. But don't forget the chain rule. You have to multiply by the derivative of that inner function, in this case, 7. So 7/3 times 7x minus 9 raised to the negative 2/3 power. And we can blast through these. I think we already know these. So we'll just quickly refresh our memory of the chain rule for a few examples, and we'll be on our way. And then normally we don't write that chain rule factor at the end. We would, put it at the beginning, maybe multiply it by the other coefficient, but you get the idea. So if we're going to try to undo the chain rule, we have to think about how that might work. Remember that when we are taking the antiderivative of something raised to a power, we can use the inverse power rule, right? So if this were just x raised to the 1/3, then I would take x raised to the 4/3 and divide that by 4/3, right? Because that's the opposite of the power rule. And just like with the chain rule, that argument shouldn't change, right? We're reversing the process. So if the argument ends up at 8x plus 1, then it should begin at 8x plus 1, right? So that we would end with the same argument. Now, if you were to try to test this, right, we've got a plus c here. If we were to test this with integration, we would say, well, we know the power rule. We bring the 4/3 out front, and the 4/3 cancels out, and the 4/3 drops by 1 to get to the 1/3. But then we also have the chain rule. And if we were to take the derivative of this, we would have to multiply by 8, the derivative of the argument. So if I multiply by 8, then I would have an extra 8 over here, which I didn't have. So I'd better make sure that that 8 cancels out. So I'll put an 8 down here at the bottom. Okay. So just like when we multiply by the derivative here, we're dividing by the derivative. We're unchain ruling it, right? So we could leave the answer like that, but that would look a little funny. We'll put the 3 on the top with the 8x plus 1 raised to the 4/3 power. We'll put the 8 times 4 on the bottom, and we'll remember our constant integration. Okay. This next one's going to work pretty much the same way. We're going to take 6x minus 5. It was raised to the 17th, so we better bump that up to the 18th power, but we have to make sure we divide by 18. That's the inverse power rule. And then we also have to divide by the derivative of the argument, so divide by 6. Remember, that's going to help us when we try to check with integration, right? When we take the derivative, the 18 will cancel out because of the power rule, and the 6 will cancel out because of the chain rule. And then lastly, we have a trig example. While the cosine integrates to the sine, and the argument never changes, 4x plus 90. But if I take the derivative of this answer, I would get 4 times the cosine of 4x plus 90, but I don't have an extra 4 out front, so make sure you divide by 4 to undo that chain rule. All right, so that's kind of the quick and easy way to undo the chain rule. And it's not always quite so quick and easy, but sometimes you can kind of just think about it and realize what's going to happen. Sometimes it's going to be a little bit more complicated. For example, if I take the derivative of this crazy beast, this is a messy argument, but it is nonetheless something that doesn't change. The power rule says we should raise that to the 4th power, but don't forget the chain rule. Chain rule is going to give us 12x to the 2nd minus 10x plus 37. All right, so the corresponding integration equation would be 5 times 4x cubed minus 5x squared plus 37x, all raised to the 4th power, times 12x squared minus 10x plus 37 dx. Well, if I'm going to take the antiderivative of this answer, it's going to take me back to here because it's just taking us back to the beginning, right? So So that's perhaps not quite as obvious if you were to just start off with this problem. And also notice that that 37 at the end couldn't be a 36 here, because then the derivative of this wouldn't match this. This 10 couldn't be a 20. We have very particular form that has to be met here, otherwise it's not going to work. So what is that form all about? The form is, if we know the chain rule and we're trying to undo the chain rule, when we take the antiderivative of some function that is a composition of functions, then we have to be very careful. We have to remember that that chain rule has to be present there as well. And when we see that, when we see the derivative of the argument inside the integral, then that means that we can go ahead and take that antiderivative. All right, so how does that process work in practice? The process is called U substitution, and the goal in U substitution is to try to rewrite the integral in terms of a new variable. So generally, we have x in our integral. It's not always going to be x, but x is the default variable name. So we have to somehow figure out what a good u value is so that we can change this in terms of x into something in terms of u. And generally speaking, the thing that equals u is the thing that's inside that g of x piece, right? That g of x piece that's inside of another function. So that x cubed plus 10 is the inner function, and then the outer function is the square root function. So look for things that are maybe in the denominator, sometimes in a parentheses, sometimes in a radical, sometimes in a trig argument, just whatever you can try. And what we're going to do is we're going to say, well, anytime I see an x cubed plus 10, I'll just replace it with a u. But here's the deal, guys. If we are taking the integral with respect to x, but we're trying to rewrite it in terms of u, then we have to not have a dx in our problem. We have to have a du in our problem. So what we're going to do is we have to figure out what du equals. Well, if we have that u equals something in terms of x, we can actually take the derivative of u with respect to x, which is pretty easy, right? We just do the power rule over here. And we can then see that du equals 3x squared dx. Okay, so sometimes we'll take this one step further, and some of you might already see what's going on here. But one thing we can do is we can say, well, I want to get rid of this dx, so I'm going to solve for dx. This is not a required step, but some people like to do it this way. So I'll divide by 3x squared and get the dx equals du over 3x squared. So that means that I'm going to rewrite this integral. That 3x squared, again, you might see what's about to happen. I'm just going to write it there anyway. Times the square root of x cubed plus 10, but I'm definitely not going to write x cubed plus 10. The whole point of this process over here was to try to get rid of the x's. So x cubed plus 10 we know is the same thing as u, and then dx is the same thing as du over 3x squared. So we have two different pieces of substitution, right? This thing right here, which equals u, and this thing right here that equals du over 3x squared. And we get a little nervous having an x squared over here until we realize that we've got an x squared over here. So actually the x squared divided by x squared cancels out. And in this case, the 3 over 3 also cancels out. I'm not so concerned about the constants because those can just be factored out, but definitely it's really important to get that the old variable, in this case x, to cancel out. So that's rewriting the integral in terms of u. So I want you to consider this integral right here compared to the original integral. This is definitely a simpler integral. Something that we definitely know how to do. We just bump the exponent up by 1, right? The 1/2 bumps up to 3/2. We divide by 3/2, which is multiplying by 2/3, and we get an integral. Now, we don't leave the answer like this because our original problem was a dx problem, an x dx problem, so we want to make sure our answer has x's in it. So we'll substitute back in what u equals, which is x cubed plus 10. So don't forget that last step. And definitely, when you do these problems, make sure that not only do you rewrite the integral in terms of a new variable, and please use u, it's just the standard way to do it. Not only are we going to rewrite the integral, we also actually have to show all of this stuff as well. We have to state what u equals. Don't make anyone guess what u equals. You actually explicitly have to write out that we're going to let u equal something in particular, and then figure out what dx equals in terms of du. And it's okay to have x's in here because generally speaking, for these problems, the x's will cancel out. All right, so we'll try another example. Well, maybe I'll move on to the next video for these examples. I don't want this video to get too long.